In the last module, we already started finding conditional distributions given the number of arrivals up to time t for a Poisson process, conditional distribution of other quantities of interest. Last time what we found was the conditional distribution of number of arrivals up to time s for s less than t, conditioned on number of arrivals up to time t, or the joint distribution of number of arrivals up to time s1, s2, etc., sk for all these times less than t, conditioned on the total number of arrivals up to time t. So in this module, we are going to look into something which is even more interesting and will be much more useful, namely, given the total number of arrivals up to time t, let's say n, where n is greater than or equal to 1, we are going to ask exactly at what points of time did this arrival took place. In other words, more explicitly, the conditional joint distribution of these n arrival times conditioned on there being n arrivals up to time t. Obviously, the joint distribution would be all these times would be random times in 0 to t. How are they distributed? So that conditional distribution is something that we'll find, and we'll see that it goes a long way in finding out many other things. It's an extremely useful joint distribution that we'll find. Okay, so this is module 17, third module in Poisson process. So we are still working on conditional distributions. As you remember, conditional distributions given the number of arrivals up to and including time n. So let nt as usual be a pp lambda, fix t positive. We already obtained some conditional distributions given nt equal to n. So what are the things that we have obtained? We obtained, given nt equal to n, the conditional distribution of ns for any s less than t, and more generally for s1, s2, sm, m many time points less than t. We have obtained the conditional joint distribution of ns1, etc., nsm. So these are the things that we have obtained. From what we have proved, they can be equivalently described in the following manner. Consider any finite partition of the time interval 0 to t, say s0 equal to 0 and s1 greater than s0, etc., sm less than sm plus 1, which is t. So this is a finite partition of the time interval 0 to t. Now for I between 1 and m plus 1, let xi I denote the number of arrivals in the interval open si minus 1 to closed si. So that is exactly the number of arrivals after time si minus 1, but up to and including time si. In other words, xi I is nsi minus nsi minus 1. So what we have proved can be equivalently stated by saying that conditional on nt equal to n, if we look at this vector, m plus 1 dimensional vector, xi1, xi2, xi m plus 1, then that m plus 1 dimensional vector has a multinomial distribution with parameters n and p1, p2, pm plus 1, where pi is si minus 1 by t. Everything that we have obtained can be described through this. So, as was already discussed, this result seems to suggest the following, that conditional on there being exactly n arrivals up to time t, these n arrivals behave as if they are independent trials, such that for each of them the probability of occurring in any interval a to b, subintervals of 0 to t, is b minus a over t. That is, the time of each arrival is uniformly distributed on 0 to t. Of course, we commented that they cannot be really independent because the successive arrival times are actually ordered. So we are now going to show that this is almost the case, except that the n successive arrival times cannot really be independent, they are ordered. So the question that we are going to address is, given the number of arrivals during time interval 0 to t, how are the times of these arrivals distributed on 0 to t? More precisely, suppose we are given that nt equal to n, we assume n is greater than or equal to 1, because if nt is 0, then everything is trivial. So this of course means that 0 is less than s1, less than s2, etc., less than sn, which is less than or equal to t, but sn plus 1 is greater than t. Question, for n greater than or equal to 1, what is the conditional joint distribution of the arrival times s1, s2, sn given nt equal to n? That's the question. We are going to address this question. So first we start with a simple case, n equal to 1. So given that nt equal to 1, that means exactly n arrivals up to and including time t, we ask what is the conditional distribution of that time of that single arrival. We know it's somewhere between 0 and t. So what is the conditional distribution? How is it distributed? So given nt equal to 1, conditional distribution of S1 is clearly supported on 0 to t, because that arrival must have happened sometime between 0 and t. So what's the conditional distribution? So towards that, we observe that for any s less than or equal to t, the conditional probability that S1 is less than or equal to s given nt equal to 1 is exactly same as the probability that ns equal to 1 given nt equal to 1, which of course can be written as the ratio of these two probabilities. That's the definition of conditional probability. And the numerator, because of independence of increments of the Poisson process, can be written this way. And then using the Poisson distribution, we can write it this way, and then after simplification, this comes out to be just s over t. So what's the upshot? What we have proved is, given nt equal to 1, the conditional probability that s1 is less than or equal to s for any s less than or equal to t is given by s over t. So you can think of that as the conditional cumulative distribution function of s1 given nt equal to 1, and that is s over t. Of course, that tells you that it is the cumulative distribution function of uniform distribution on 0 to t, which therefore means that given nt equal to 1, the conditional distribution of S1 is uniform on 0 to t. So given that there is exactly one event up to time t, the time of that event, the time of that arrival, is uniformly distributed on 0 to t. That's exactly okay. So we next consider the case of more than one arrivals during time 0 to t. But to handle that, we need to use two basic results from probability. Result 1 is this. Suppose y1, y2, yn is a random vector taking values in some region D in Rn. Suppose that f is an n-dimensional probability density function on D. That means that f is a non-negative function on D integrating to 1. Integral of f over d is 1. So f is a probability density on D, such that if you take any point y1, y2, yn in D, then look at the probability that capital Y1 lies in y1 to y1 plus h1, etc. yn lies between yn to yn plus h. Divide that by h1, h2, hn. Then as h1, h2, etc. hn decrease to 0, suppose this ratio goes to the function, a value of the function f at y1, y2, yn. Now if this happens for every y1, y2, yn in D, then this function f has to be the joint density of the random vector y1, y2, yn. So that's a basic result in probability. In one dimension case, this essentially says that well, in case there is a density, that is, if the derivative of the cumulative distribution function exists and is a probability density function, then that must be the density of the distribution. So this is just an extension of that to higher dimension. Result 2 is that about order statistic. So suppose z1, z2, zn are IID with common density g on some interval a to b, then z bracket 1, z bracket 2, z bracket n obtained by ordering z1, z2, zn in the increasing order, called the order statistic, has the joint density given by this f z1, z2, zn is for z1 less than z2 less than zn, it is product of zi from I to n, but then multiplied by n factorial. Okay, so now we come to our main problem, finding the joint distribution of s1, s2, sn given nt equal to n. Clearly, given nt equal to n, S1, S2, Sn, this n tuple takes values in this region, namely that T1, T2, Tn, such that 0 is less than T1, etc., less than Tn, less than T. So surely we know that S1 is less than S2, less than Sn, less than T. So the vector S1, S2, Sn takes values in this region. So what we are going to do is we will use result 1 to show that the conditional distribution of S1, S2, Sn given nt equal to n has a joint conditional density on D, and this we'll do by using result 1. So fix any T1, T2, Tn in D. That means you have taken a n tuple satisfying T1 positive, T2 is greater than T1, etc., etc. Tn is greater than Tn minus 1 and Tn is less than T. Now having fixed such a point T1, T2, Tn in D, let H1, H2, etc. Hn be small enough so that this is true. Of course, given T1, T2, Tn which are strictly increasing, you can always find H1, H2, Hn satisfying this property. Now consider the event A which of course I simply call it A, but it depends on T1 to Tn and also H1, H2, Hn. So this is the event that Si for I equal to 1 to n lies in the interval Ti open to closed Ti plus Hi. So what we are going to do is, we first evaluate the probability of this event A given nt equal to n. By definition of conditional probability, this is of course probability that A intersection nt equal to n divided by the probability nt equal to n. Now we denote, for the sake of notation, we denote Tn plus 1 equal to T. Let's see figure A. Okay, so from this figure you can easily see that the event A intersection nt equal to n simply says that nt1 equal to 0 and then nti plus hi minus nti equal to 1, because the S1 lies between T1 and T1 plus H1. Similarly, n T2 plus H2 minus nt2 is equal to 1, etc., etc., and nti plus 1 minus nti plus hi equal to 0. So convince yourself that the event A intersection nt equal to n is exactly this. So using properties of Poisson process with rate lambda, we can easily obtain this probability to be, so we use first of all independence of increments over disjoint intervals and the Poisson distribution of increments. Using both these things, that probability turns out to be exactly this, which after simplification gets to exponential lambda t minus lambda t times lambda to the power n into product I equal to 1 to n hi. But remember that probability nt equal to n is simply the Poisson probability mass function at n, Poisson parameter lambda t. So it's given by exponential minus lambda t to the power n over n factorial. So if you now divide the joint probability of A intersection nt equal to n by the probability nt equal to n, you get the conditional probability to be this, which simplifies to this. Now if you divide this by the product of h1, h2, hn, and you immediately get the product h1, h2, hn gets cancelled, so you end up getting just n factorial by t to the power n. So there is no h1, h2, n left anymore. So the limit of this as h1, h2, hn tends to 0 would be just n factorial over t to the power n. So now use result 1 to conclude that given nt equal to n, the conditional joint distribution of S1, S2, Sn has a joint conditional density, and the density is given by conditional joint density of S1, S2, Sn given nt equal to n is given by f S1, S2, Sn given nt equal to n at a point t1, t2, tn is n factorial by t to the power n for 0 less than t1 less than t2 etc. less than tn less than t. So this is the conditional joint density of S1, S2, Sn given nt equal to n. So we conclude, now we use result 2, that given nt equal to n, so if you look at this density, this is just the joint density of the order statistic based on n IID uniform 0 to t random variables, because each of them has density 1 over t. So this is the product of 1 over t n times, but then n factorial. So that's exactly how the order statistics joint density is defined. So we conclude this, that given nt equal to n, the n arrival times S1, S2, Sn are conditionally jointly distributed as order statistic obtained from n independent identically distributed uniform 0t random variables. So what we have just proved can be described as follows. Suppose we are given that there are exactly n arrivals up to time t. Given this, here is how the n arrival times S1 less than S2 etc. less than Sn less than t are conditionally distributed. So let E1, U2, Un be n independent random variables distributed uniformly on 0 to t. Consider the order statistic based on U1, U2, Un. Call them U bracket 1 less than U bracket 2 less than U bracket n. So this is the order statistic based on this IID uniform 0t random variables U1, U2, Un. Then given nt equal to n, the conditional joint distribution of the arrival times S1, S2, Sn is the same as the joint distribution of the order statistics U bracket 1 etc. U bracket n. So S1, S2, Sn conditional on nt equal to n behave exactly as if you have picked n IID uniform 0 to t random variables and ordered them. So this has some interesting applications. So let's see some nice interesting applications. Start with example 1. So suppose arrival at a server occur as a Poisson process with rate lambda. That means successive arrivals take place and that arrival process behaves like a Poisson process with rate lambda. Suppose the server is supposed to remain down for some time period t, and customers who arrive during this period would have to wait until the server is up and running again. Okay, so there is a time period t during which the server will be down. So customers who arrive during that period, they would have to wait until the server is up. So what we want to know is what is the expected total waiting time of all the customers arriving during the down period. Of course, time starts from the instant the server goes down. The server remains down till time t. Nt customers arrive during the time period where nt is a Poisson process, and the ith arrival waits for time t minus si. Si is the time when the ith arrival arrives, and t is the time starting from 0 when the server is up again. So for the ith arrival, the waiting time is t minus si. So the quantity of interest for us is, I look at all these t minus si's for all the arrivals up to time t, and then take the sum, expected value of that. So that's the quantity of interest. So what we do is, to find the expected value, so the sum is from I to nt, which is random, and then the summands are also random because the si's are random. So we first condition on nt, fix n greater than or equal to 1, because if nt is 0, the sum is 0. So fix n greater than or equal to 1. We find the conditional expectation of this given nt equal to 1, nt equal to n. So conditional expectation of I equal to 1 to nt, t minus si given nt equal to n is, of course, since we are given nt equal to n, this is the sum from I equal to 1 to n, t minus si, nt equal to n. Clearly, the first term in the summands t, they are constants, so they come out. So there are n many of those. So that gives you nt minus expectation of I equal to 1 to n si given nt equal to n. Now we make use of the fact that given nt equal to n, the S1, S2, Sn are conditionally distributed as the order statistics u bracket 1 etc. u bracket n based on NIID uniform 0 to random variables u1, u2, un. And of course the sum of the order statistics is the same as the sum of the original statistics. So this basically gives that, first of all, the conditional expectation of summation si I equal to 1 to n given nt equal to n is the same as using the fact that conditional joint distribution of S1, S2, Sn is the same as that of the order statistic. So this is the same as the sum of the n order statistic based on NIID uniform 0 to random variables. But the sum of order statistics is the sum of the original random variables. And now we have a sum of bunch of uniform random variables on 0 to t. Each has expectation t over 2. So this is nt over 2. So that implies that the original quantity that we had, namely the conditional expectation I equal to 1 to nt of t minus si given nt equal to n, turns out to be nt minus nt over 2, which is nt over 2. Now this is the conditional expectation. Now we have to take the weighted sum of these things with multiplying these things by the probability that nt equal to n. So you can do all of that, and it turns out that this is expectation of t into nt over 2. And since nt has expectation lambda t, because nt is a Poisson random variable with parameter lambda t, so expectation of nt is lambda t. So putting that in here, you get this quantity of interest, turns out to be lambda t square by 2. So this is a nice application of that conditional joint distribution of S1, S2, Sn, given that there are n arrivals up to time t. Let's see one more application. This is a nice application. This is example 2. Suppose there is a one-way expressway and cars enter that one-way expressway through a toll gate, and they enter this according to a Poisson process with rate lambda. So the arrival of the first car to the toll gate, then there is an arrival of the second car, third car. So this arrival process is a Poisson process with rate lambda. Now on entering the toll gate or entering the expressway through the toll gate, each car assumes a random velocity independently of the time of its entry at the toll gate and continues running on that velocity throughout the expressway. What we assume is that the velocities assumed by different cars are also independent random variables with a common distribution of f. So each car on its arrival at the toll gate assumes a random velocity which is independent of the time of arrival, and moreover the velocities assumed by different cars are independent and identically distributed with a common distribution f. Suppose now there is a bridge on the expressway at a distance of alpha from the toll gate. So what's the question we ask? We ask, at time t positive, how many of the cars that have already entered the expressway are yet to reach the bridge. To be precise, for t positive, let yt be the number of cars that have entered the expressway by time t but are yet to reach the bridge at time t. We want to find the distribution of the random variable yt. So let's denote nt to be the number of cars that entered the expressway by time t. Then nt, of course, we know is Poisson with parameter lambda t. For k greater than or equal to 0, what does the event yt equal to k mean? Remember, yt is the number of cars that have entered the expressway by time t but are yet to reach the bridge at time t. So that number is k, means that, of course, at least k cars must have entered the expressway by time t, that is nt is greater than or equal to k, and out of the cars that have entered, exactly k are yet to reach the bridge at time t. Now note that the ith arrival before time t will not reach the bridge by time t if and only if vi, the velocity assumed by the ith arrival, multiplied by the time that the particular car has run up to time t, which is t minus si, because the arrival time is si. So velocity multiplied by the time through which the car has run, time up to time t, if that quantity is less than or equal to alpha, then the vehicle will not reach the bridge at time t, where si denotes the time of the ith arrival and vi denotes the velocity assumed by the ith car. So therefore, probability that yt equal to k is same as probability I equal to 1 to nt, indicator of vi into t minus si less than or equal to alpha, that sum should be equal to k, because that indicator is 1 or 0 according as the ith arrival has not reached the bridge or has reached the bridge. Okay, as in the previous example, we condition on nt and use the result that given nt equal to n, the arrival times s1, s2, sn are conditionally distributed as the order statistics u bracket 1, etc., u bracket n based on n IID uniform 0 to 3 random variables. This gives for any n greater than or equal to k, remember, in order for yt to be equal to k, nt has to be at least k. So for any n greater than or equal to k, probability that yt equal to k given nt equal to n is the same as, firstly, probability that summation I equal to 1 to n of those indicators equal to k given nt equal to n. But then, now using the fact that s1, s2, sn conditional on nt equal to n are exactly same, jointly exactly, have the same distribution as the order statistic, that probability, that conditional probability is same as this unconditional probability. Now, how do we compute this probability? To compute this last probability, this is how we proceed. Consider n independent uniformly chosen random points u1, u2, un in 0 to t, and let v1, v2, vn be IID with common distribution of f. These are the velocities, and v1, v2, vn are not only IID among themselves, but they are also independent of u1, u2, un. Call a point ui a success if vi into t minus ui is less than or equal to alpha and a failure otherwise. Clearly, the above probability, namely the probability that summation I equal to 1 to n indicator vi t minus u bracket I less than or equal to alpha, that sum is equal to k, that probability is then the probability that there are exactly k successes among the n points. Because if you go back to the definition of that indicator is 1 if the point ui is a success and 0 otherwise. Of course, this is with order statistic and ui's are not order statistic, but the count of the number of successes, whether it's with order statistic or whether with the original statistic, wouldn't make any difference. That's the whole issue. So this above probability therefore is a probability that there are exactly k successes among the n points. Now note that for each point the probability of being a success is so here I use generic notation, all the ui's have the same distribution, all the vi's have the same distribution, and the vi's are independent of the ui's. So this would be the probability that v into t minus u is less than or equal to alpha, which is same as the probability that v is less than or equal to alpha over t minus u. Now you can condition on u, which is uniform on 0 to t, and then condition on u, the probability that v is less than or equal to alpha over t minus u, given u equal to u, that is simply, it can be written in terms of distribution function. But note that if u is uniform, then t minus u also is uniform. So we can replace u by t t minus u. So you end up getting this probability to be equal to 1 over t integral 0 to t f of alpha over u du, and let's denote that number by pt. So that's the probability of, for each point, any point, this is the probability of being a success. And we are asking what's the probability that out of n there would be k successes, and that's exactly the conditional probability that yt equal to k given nt equal to n. So it turns out to be the binomial probability n choose k pt to the k into 1 minus pt to the n minus k. Since the probability yt equal to k, we wanted the unconditional probability, is simply the conditional probability multiplied by the probability nt equal to n summed over all possible values of nt, which in this case has to be n greater than or equal to k. So you can write this, we have already obtained the conditional probability, and the probability nt equal to n, we know it's the Poisson lambda t probability mass function at n. So one can write this down, do some algebra, and one can easily deduce that probability yt equal to k, once you compute that for any k greater than or equal to 0, it will turn out that the distribution of yt is again a Poisson distribution with parameter lambda sub t, where lambda sub t turns out to be this quantity, lambda into 0 to t integral capital F alpha over u du. So this is again another application of that phenomenon, that fact, that conditional on there being exactly n arrivals up to time t, the sequence of these n arrival times, successive arrival times, behave like the order statistic based on n IID uniform random variables from 0 to t. So in this module, the first most important thing that we found was that conditioned on there being n events up to time t, n arrivals up to time t, where n is greater than or equal to 1, we showed that the conditional joint distribution of the successive n arrival times are distributed exactly like the order statistic based on n IID uniform 0 to t random variables. In other words, given that there are n arrivals up to time t, assume n is greater than or equal to 1, if you want to understand what was the distribution of the conditional distribution of the n arrival times, it's like this. Pick n points uniformly and independently from 0 to t, order them, get the ordered statistic. The distribution, the joint distribution of this ordered statistic exactly gives you the conditional joint distribution of S1, S2, Sn, conditioned on nt being equal to n. And then we saw how to apply this in two applications. In both cases, we were actually, at some point of time or other, we actually made use of this conditional distribution. So essentially, we were asked to find some probability or some expected value. We conditioned on the number of arrivals up to time t, and after that conditioning, invariably the joint distribution of the arrival times up to time t, conditioned on the total number of arrivals, was somehow made to use.